All right, test 1 2. Test 1 2.
I can hear you now.
Can hear now? Okay, can you guys hear now? All can hear? If you can't hear, turn that like volume button up on your computer. You know. All right, good now. I don't know what was going on there. Okay, reminder, homework number 2, due Monday, beginning of lecture. Final draft of your lab report, due the day that you have lab at the beginning of lab time. That's the announcements. Okay, let us begin. Mic check, 1 2. Where are you going to run? Maybe we could meet up on the sun. If anybody knows that group, I'll be very impressed. Anyone knows the lyrics from that song? I'll be very impressed. All right. Let's talk about where we left off. We were making a transition from looking at two-dimensional stress transformations to 3D stress transformations. So let's do that. Okay, we'll kind of remind ourselves where we were and then pick up from there. So remember in 2D, you had an element that looked like this. It had stress components sigma x, sigma y, and also your shear stresses. Here, we made a cut on this particular object that looked something like this. And that allowed us to look at this cut element that still has kind of this x and y coordinate system, but now has a normal and tangential axes coming off of it. So here we have n and t. And when we have the normal and tangential axes now, we have stresses in the normal direction and shear stresses on the normal face in the tangential direction. So we have a normal stress here, and we have a shear stress tau and t on the normal face in the tangential direction. We saw that this was balanced with a force balance by the original stress components that still existed sort of on the bottom side of this particular element. And so when we did some of the forces in the end, we've established the normal stress equation, which was something like sigma x cosine squared theta plus sigma y sine squared theta plus tau, or 2 tau, x, y, cosine theta, sine theta. This is your stress transformation to go from stress values that you already knew, things like sigma x, sigma y, and tau xy, to normal stress in a new coordinate system, this nt coordinate system, which has been rotated through by this angle here of theta. Okay. We looked at the variable normal stress that might exist given variable values of theta. And we said that if you took the derivative of this particular equation, set to 0, you can determine max and min stresses. And similarly, we had a transformation to get us the shear stress, tau nt. We take that, derivative set to 0. This helps us determine the max and min shear stress. Okay, at that particular point. Now, what I mentioned, kind of at the close of last lecture, where we were going, is that we're going to do a similar sort of thing, where we have an established state of stress cut through our element, and then have some derivation that tells us what is the normal stress on the cut face. But now we're not going to do it in 2 dimensions, we're going to do it in 3 dimensions. So let's kind of pick up where we did, sort of where we left off last time. I feel like I'm advertising a movie. Now in 3D. You gotta wear like those stupid glasses when you watch the movie. Yeah, okay. No, you don't have to wear stupid glasses when you watch my lecture. So if you put those like red and blue glasses on, I bet it would probably help. Like, why not? Okay, so now in 3D. And remember our 3D stress cube? Was the following. Where stress at any particular point can be represented by 9 stress states. 3 in the normal direction. Here's your sigma y, sigma x, sigma z. And then you have 6 shear stress components, 3 of which are redundant. They're from the Department of Redundancy Department. Okay, so here you have tau on the y face in the z direction. Here you have tau on the y face in the x direction. Here you have tau on the x face in the y direction. Here you have tau on the x face in the z direction. Here, tau on the z face in the y direction. And here you have tau on the z face in the x direction. All right, so these are all your stress states that could possibly exist. This is like the analogy of the 2-dimensional square that had sigma x, sigma y, and tau xy. All right. So now we're going to cut this. Sort of in an arbitrary manner. And we'll slice through to create some surface that looks like this. And if you can imagine that those sort of coordinates are still sort of running through the backside of the cube here, this is the cut that we make. Now, when we make that cut, we can define stresses on this sort of like tetragonal element that we make, and we can define geometry on the tetragonal element. We will need both of these things for our derivation. So let's first maybe define sort of the geometry of this tetragonal thing. Okay. So this geometry of this tetragonal thing starts with, we have a normal off of the face which we cut through. All right, so just like with our 2D element, we had like this normal coming off of the surface. We have the same idea, is that we've cut through this face and we have a normal coming off of that face, but now in 3D. Okay, so that normal coming off the face, maybe I'll draw it in blue, sort of looks like this. The normal stress coming off of this face. And maybe this kind of comes back to sort of the center point. All right. So that's the normal coming off of that particular face. That normal makes an angle with the x, y, and z axes, which we can define using things like theta y, the angle between the x-axis and the normal. Here this might be theta x. And between the z-axis and the normal, theta z. All right. We then defined directional cosines that helped us assign that normal. So direction cosines. Would be something like L is cosine theta x, M is cosine theta y. Bring this down only a little bit. And N is cosine theta z. All right, should harken back nightmares of your statics days, right? Using direction cosines to define unit vectors, where here the new unit vector is like the n direction. Right? All right, so this is like the geometry. All right, we can also define the stresses on this new cut face that we have. Okay. The whole point of what we're doing is to come up with an expression or an equation for the normal stress on this cut face. So obviously we're going to have on this like oblique face that we've just created some normal stress sigma n. Okay. We're also going to have shear stresses on this face that we have to sort of define arbitrarily at this point. Okay, so we have a shear stress also acting on this face. And not only do I have one, but we have two of them. So a shear stress acting on this face on what would be the normal face, so on the end face, and what I'll say the T1 direction. Okay? And here we have shear stress acting on the normal in the T2 direction. All right, James Cameron style. T2. Starring Arnold Schwarzenegger and Linda Hamilton. Yes. Come on. That's a pull. That's a pull for you. Linda Hamilton. Man. One good movie ever. Okay. So those are the stresses that are on kind of like this normal face. All right. But those are balanced by the stresses that are on the back half of the cube that still exist. So remember on the back half of the cube, and I'll sort of draw them in blue, because they're on the back side. They're so sad. They're blue. All right. Okay, your normal stresses, and those are coming off of like the back areas of this cube. And then you would also have shear stresses sort of on that back area. A little bit difficult to draw in this figure, but hopefully you sort of understand kind of what's going on with the shear stresses on that back face. Right? I'm not going to label them, but it's things like tau xy, tau xz, and tau yz. All right? So the whole point here, I'll leave this up for a second, those copying. Is we want an equation for the normal stress on that sort of tetrahedral face that we've created. Okay. Who remembers how we did this in 2 dimensions? Anybody remember how we got an expression for sigma n in the 2D element? It rhymes with rum the horses. Anyone, audience?
Sum the forces.
Sum the forces. Okay, I got it in my ear. Good. All right, we want to sum the forces in the normal direction, set it equal to 0. We don't want to rum the horses. That sounds awful. Let's sum the forces in the normal direction equal to 0. So to do that, we more or less have to translate all of the stress elements that we see on that cube into forces. So need to write stresses, let's just call them stress ij, in terms of forces in the normal direction. Okay? And the general way that we're going to do that is with, the expression that you learned in your Wayback Machine, that the stress is equal to the force times the area, or the way that we're going to write it is equal to the force, because we're going to be working in terms of forces, is the stress times the area. So that means I need to define some areas back in my geometry figure to help me define the areas on which the stresses act. Okay, so let's go back up to our geometry and talk about the areas. I'm going to arbitrarily assign the area of the face that I cut as the area dA. So this area here, which is sort of like the area of this cut face here, is dA. From that, I can define the areas on the back side of the cube by multiplying dA by the associated directional cosine to determine the areas on sort of the back face of that cube. So what do I mean by that? Okay, there's dA, but if I'm interested in like the area on the back face, which might be like this area is sort of on the back face here of this particular cube. Hopefully we sort of see that area, kind of on the back side of that tetrahedron. This is like dAy, because that is the area that's sort of on the back side y direction of that face. Hopefully we can see that. That dAy is just going to be dA, which is the full area of that tetrahedron face that I sliced, multiplied by the directional cosine, m. So dAy is simply dA times m, the directional cosine. Tells us like the amount of area that is sort of projected onto the the xz plane from the original dA quantity. All right. So now we're about ready to do our sum of the forces. Right. All right. In the n direction, obviously, I will have my stress in the normal direction times the area over which that stress acts. Okay, so this is the force in the normal direction from sigma n. All right. Now I have to look at kind of these other components. And let's just start with, let's say, the sigma x component, right? That sigma x component is acting kind of on the back face of that tetrahedron, and it has an area associated with it that's like dAx, which is dA times cosine of theta x, or dA times L. Okay? So this is sort of acting in the negative n direction. And the amount of stress that we have is sigma x, and the component of that stress that's along n is multiplied by the direction cosine L. And the area upon which that stress acts, I need a force times an area, is the original dA multiplied by the projection of that area onto the back of that cube, which is L. Okay, so let's make this clear. This is the stress projection onto n, and this is the areal projection onto n. And we can do that with all 9 stress components. All right, we've got a normal stress in x, normal stress in y, normal stress in z, and then we've got the 6 shear components that each have some directionality associated with that we need to project into the n direction, and some face that they act upon, which also needs to be projected into n. So let's do that. The remaining normal stress components will look similar. This is sigma y times m multiplied by dA times m. Similarly with the stress in z. Okay, so those are my normal stress components. Now my shear stress components, let's maybe start with an easy one. Tau xy. I have to project this into the n direction, and it's acting on the x face in the y direction. It's acting in the y direction. So to project it properly into n, I must multiply it by m. Multiplied by the area on which that stress acts. So it's acting on the x face, so we need to project it from the x area onto n. This will be dA times n. That's because the shear stress acts on the x face, so we need to project it to n. And it's acting in the y direction, so its component of stress needs to be projected with the directional cosine m. And we can repeat this for basically all of the shear stress components. So here we have tau yx. We need to project the stress by the directional cosine n, multiplied by the area on which we act, multiplied by m. Is that right? No, that's not right. Yeah, that's correct. Yeah, it should be the L. Right. Yeah. Yeah, that's right. You're right. Okay, so this should be acting on the x face in the y direction. Right. DAL, correct. On the x face, this should be dA times L. Thank you. Acting on the x face in the y direction. Correct. Okay. So apologies for that. So that's x on the y face. So m is correct. And projecting into L, this should be an L. Okay. Minus, here we are, tau, continuing on, xz, multiplied by acting on the x face in the z direction. So we need to project it using n, dA times acting on the x face, so multiplied by L. Tau on the z face in the x direction, so this is times L, multiplied by dA times n. Right. Finally, yz, this will be multiplied by n on the y face in the z direction. Need to use the directional cosine in n, multiplied by the area projecting into the y direction, which is m. I think the notes are incorrect, so make sure you update here appropriately. Finally, here times m, and projecting into the z-plane, which is n. Okay, that's correct. Yeah, that's right. Okay, this all equals 0. So each one of these is a force. It's a stress multiplied by an area. So we've sort of projected the components of the stress into the n direction, and we've projected the area from our original slice into the n direction as well, the direction of the normal face. Okay, so all of these contain a dA term, so all the dAs are going to go away. And we also know that like tau xy is equal to tau yx and so on. So we'll cancel dA and let tau ij equals tau ji. We know that from conservation of momentum. Then we rearrange to get the following. The normal stress is sigma x L squared plus sigma y m squared plus sigma z n squared plus 2 tau x y L m plus 2 tau x z L n plus 2 tau y z m n. Okay, this should all be correct. So here's your equation for the stress on any arbitrary face, given values of stress that you may have already known, sigma x, sigma y, sigma z, tau xy, tau xz, tau yz, as well as the angle that your new normal axis makes with the original coordinate system, which you can define with direction cosines L, M, and N. Okay? there you go. Normal stress on cut face in terms of stresses you knew or assumed to know. And the angle that your normal makes with the original axes. Which might be given to you as sigma x, sorry, theta x, theta y, theta z, or converted to directional cosines. Appropriately. This is very similar to 2D, except you just got more stuff. You got more angles, you got more stress components, and you have more stress. Just what you need. More stress in your life. You need more stress, but you don't need more circle, which is horrible. Okay? So, that's your stress transformation equation. All right? We would like to show that this equation, if simplified to 2D, would give us our original two-dimensional stress transformation equation. Okay, that would sort of like help us verify that what we've done here is correct. So let's check the simplification to 2D because, you know, math is fun. Okay. So recall in 2D, we had that the normal stress is sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau x y sine theta cosine theta. That was our two-dimensional stress transformation equation. Okay. Going from like an xy coordinate system to an nt coordinate system. This is the single angle formulation. Right. And remember that when we did 2D, we assume, it looks like ZD, in 2D, we assume plane stress. Okay, and plane stress means that we don't have any out of plane normal stress component or any contributions to shear from out of plane components. Right. Okay. Also, in 2D, remember we're going from like, it's like an x, right, to like nt, right? So the angle that the normal makes with the x-axis, this is like your theta x, okay? The angle that the normal axis makes with y, this is like here, your theta y, right? Which we know here is like 90 minus theta x if we're in 2 dimensions. So in 2D, we have the following situation. L is cosine theta x. M is cosine theta y, which is cosine 90 minus theta x, which by trig is just sine theta x. Trig, word. All right, so let's look at our 3D equation and make sure that it simplifies appropriately to the 2D expression. So here's your 3D. Let's get rid of the stress components that don't exist in 2D. So we know this guy is 0, this guy 0, this guy 0. Okay. L is cosine theta x. M is sine theta x. Which is exactly the stress transformation for 2D. All right. So it works. I feel better. Do you feel better? Yeah, we're all happy. I know you're all like worried, like, oh my gosh, does this simplify to 2D? I can't handle the truth. Okay, Tom Cruise style. You can't handle the truth. So that's good. We verified here that the 2D expression for stress transformation can fall out of the three-dimensional expression. So that's good. All right. Now that was the normal stress. Now let's say that we want an expression for the shear stress on that cut face. Okay. So what about the shear stresses on the oblique plane? So remind ourselves our little, you know, trapezoidal geometry here. I don't know what you want to call this. Is it a trapezoid? No, it's not a trapezoid. What is a quad it's not a triangle because it's like a three-dimensional body.
Prism?
A prism? Yeah, what kind of prism? It'd be like a there's a name, a specific name for this structure, a tetrahedron. Okay, yeah. That's a tetrahedral figure. Okay, that's what it is. Okay. So yeah, this little, tetrahedral figure, etc. We're curious about the shear stress on the oblique plane. All right, so we already looked at what is this like normal stress, sigma n, and we just derived an expression for that in terms of sigma x, sigma y, sigma z, tau xy, blah, 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 blah. But now we want these like shear stresses on this face as well. Okay, something like tau n t2, and here tau n t1. If we're assuming here that we have sort of these t1 and T2 axes that are sort of like lying on that oblique face. All right. Now the question is like, how do we define the directionality for T1 and T2? I mean, why did I draw them in that way? Why didn't I draw like rotated some arbitrary amount from that? Okay. And the question is like, when you make this oblique cut, the normal direction is obvious to define. Okay, that's just the axis that comes off of the cut that you make. But the t directions here more or less have infinite possibilities for orientation. So let me make that perfectly clear right now. Okay, I'll say the shear stresses tau n t1 and tau n t2 depend on the orientation of T1 and T2 axes. Okay? With this oblique cut that we've made, T1, T2 axes have more or less infinite orientation. Okay, we could spin that T1, T2 axis and orient it in a million ways. Okay, so I'll say here, but the orientation of T1 and T2, you have infinite possibilities. Okay. So, I've drawn them on this tetrahedron up here as like T1, kind of up and to the left, and T2 a little bit down and to the left. But I could have just as easily said, like, okay, this is T1, and like this is T2. Okay, there's nothing stopping me from just arbitrarily assigning T1 and T2, right? So you need some quantitative method to properly assign like a T1 and a T2, okay? There are ways to do it, but it's a little outside the scope of this class, okay? It involves some three-dimensional math and pointing more or less to what is the greatest orientation for the shear stress to occur. So it's a little bit outside of what we can really cover in this class. But I'll say, in this class is the best we can do is determine max shear stress on the face. Okay? The derivation has to do with more or less the gradient of the shear stress field on that face. Okay? So when we think about finding the maximum and minimum of a function, we take the derivative, we set it equal to 0. In 3 dimensions, you take the gradient and you set it to 0 to sort of define where you have your maximum orientation for your various shear strains. Okay? I'll say that the derivation has to do with the gradient of the shear stress that you calculate. So the way that this goes is you basically arbitrarily align a t direction, calculate what is tau nt. So basically, method. Arbitrarily assign t direction to find tau nt. What would be the shear stress on the end face in that arbitrary t direction that you assigned. All right. Then sort of vary the orientation of t to see how nt changes. Okay. So as I'm sort of arbitrarily shifting the t direction on that end face, I'm going to have various magnitudes of that shear stress tau nt. Okay. So more or less, you just calculate over and over and over. Okay, what is tau nt if my t direction is here, 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 anywhere? Okay, not the genie from Aladdin, but t direction here, t direction here, t direction here, and you just see how it changes. This is related to the gradient. So I'll say there's a lot of math behind this, but the basic idea is you're taking the gradient of this tau nt as the rotation angle of that t direction changes, and we can find that the maximum shear stress on the face after some math is given by the following. And all of this to the 1/2 power. Oh, sorry, I missed a square. All of this to the 1/2 power. Obviously. God. So, it was so intuitive. Okay. That's like your maximum shear stress condition. If you plugged in plane stress, conditions, again, sigma z is 0, all the associated angles with N, M, and L are what they're meant to be. This would converge to the maximum shear stress equation for two-dimensional. Okay? This form of the max shear stress equation is known as the octahedral shear stress equation. Why is it called the octahedral shear stress equation? I'm so glad that you asked. Well, think about the sort of the cut that we made with our little, tetrahedral face. Here's X, Y, Z. And we made sort of this guy here. Yes? This particular face has a maximum shear stress on that face, tau nt, given by the equation above. So maybe that's here. Right? There are 7 other faces that look a lot like this face that have that same maximum shear stress. Okay? We're looking more or less at the entire positive XYZ quadrant, or octant, as it would be. Right? You could understand that if we moved our three-dimensional cube into, let's say, positive x, positive z, but negative y space, we might be able to draw something that looks like this. All right. Okay. Where our triangular element now is sort of on this sort of back face. Okay, it's a little bit hard to sort of envision, I guess, but did I do that right? Yeah, that's right. Yeah. Okay. So I have sort of on this kind of back face, a little bit difficult to sort of understand, but here, this face. Okay. This also has a max shear stress associated, say here, because this has a normal coming off of it, N. This guy has a normal coming off of it, N. These two are equal. Right? And I have possible 6 other sketches that could look like this. So it's called the octahedral shear stress because it's equal as long as sort of this oblique cut that you make in the coordinate system quadrant or octant that you're in has the same sort of general, I don't know, shape. It's the best I can do. And then there are, besides this, 6 other instances. 8 total. All right, that's why it's octahedral shear stress. Okay, we'll stop here today. That'll be it. And then we'll pick it up on Monday, talking about taking the derivative of this 3-dimensional equation to get the principal stresses, just like we did in 2D. So that's it for today. Thanks for coming. Enjoy your weekend. Email me if you got questions, RAR, etc.